The objective of this short tutorial is to talk about how to read this sample size estimation table. In the table, there are four basic concepts that go into estimating the sample size. There is the effect size, there is alpha, power, and the correlation between two events that as in analysis of covariance, we can reduce. The objective of this tutorial is to talk about estimating sample size. We're looking at sample size estimation in the context of a continuous outcome variable, say blood pressure or weight or something like that. The environment in which we're testing this is when we're comparing two different groups. So it's discrete groups to as in an independent t-test or an analysis of variance with an unadjusted paired comparison, or adjusted actually if you change the alpha level. So we also consider the situation where we have analysis of covariance, which is used to reduce the variability between subjects. And in that case, we're going to add the factor of correlation between groups. This can also be used to help us with paired t-tests as well. So there are four components that we're worried about. One is effect size. As we know, the effect size is the mean of one group minus the mean of the other, divided by the standard deviation. And I have highlighted Cohen's three main effect sizes that he talks about: small, medium, large, corresponding to 0.2 standard deviation effect size, 0.5, and 0.8. Now, if we look at this chart, we can see that there are basically three columns. The columns differ based on the power that we're looking at. So all are alpha 0.05, and alpha is the type 1 error, and that refers to the null hypothesis. What's the probability of incorrectly rejecting the null when the null hypothesis is true? Power refers to our probability of correctly rejecting the null hypothesis. And we have a power of 0.8, which means 80% of the time, if we run a study, the distribution will allow us to reject the null correctly. 20% of the time, we won't reject the null hypothesis and make a mistake, a beta error. So we have three columns: power of 0.8, 0.9, and 0.95. In this third column, alpha error and beta error are equal. So beta is 0.05, leaving a power of 0.95, and alpha is 0.05. So this is considered the minimal set of conditions, where alpha is 0.05 with a power of 0.8. Now we add one more condition to this, and that's the correlation. If the two groups are completely independent, the correlation is 0. There's no relationship between the two. As the correlation between groups increases, or as your covariate, if you add a covariate to the study and it has it's correlated with the outcome variable, we can adjust the sample size based on the degree of correlation. An R of 0.7 is equivalent to a R squared, or percent of the variance accounted for, of 0.5, well, 0.49, close to 0.5. So you're accounting for about 50% of the variance with your covariate in terms of a paired t-test. The two variables share about 50% of the variance. So if you have a situation in where you're looking for a half standard deviation difference, and the groups are independent, so the correlation is 0, and you're interested in alpha of 0.05 and a power of 0.8, you need 63 subjects per group. If you have a covariate and it's correlated at 0.7, you need 32 subjects per group. You can see adding a covariate is very useful, a very useful technique. So effect size is an interesting thing. Sometimes we get variables. So let's say our mean IOP is 18, and in a control group study, a literature review, and we see that the standard deviation is 0.6, or is 6 rather. So mean of 18 with a standard deviation of 6. We would say if we were doing a drug that reduced IOP, we might want to find at least a 0.5 standard deviation difference. So that would be 3 points. Half of a standard deviation is 3 points, since the standard deviation is 6, and we would have that sample size that we were just talking about. If we wanted to see what a half standard deviation difference is, and we wanted the alpha to be equal to the power, instead of a power of 0.8, we have a power of 0.9, then we go all the way up to 104 subjects per group. You can see this is getting to be a pretty big study, and that's why people don't do a power of 0.95 very often. They do a power of 0.8, although that means that they have a chance, a 20% chance over on this end, of making an error, of not rejecting the null hypothesis when it's true, failing to find the cure of cancer, for example. Whereas over here, you only have a 5% chance of not detecting that cancer cure of at least a half a standard deviation. So that's how you read this sample size table. Good luck. Correlations go down this column, these columns, and the general columns are equal at alpha 05.8, alpha 05.9, alpha 05.95 with a certain correlation and a certain effect size. That's it. Thank you.